So, welcome to this new lecture. In the last part, we covered the particle in a 1D box or the deep square wave potential. So, in this lecture, we will be discussing the particle in a 3D box and degeneracy. So, the flowchart of the lecture will be, first of all, we will solve every equation of the 3D Schrödinger's equations and setups. And after that, we will talk about degeneracy. So let us start. So first we will go with drawing a cubical box, that is a 3D box. So let us suppose this is a square of equal lengths. Just a second, just copy it. So this is a square box and this is a cube, and let us take it as x, this as y, and or not this, let us take this one x, this one y, and this one z, and let the length of all the vertex of this cube are equal and the length of vertex equal to L. So now we will move on with the three-dimensional Schrödinger's equation, that is the time independent one. So three-dimensional time independent Schrödinger's equation. So it is minus h cut square by 2m del 2 phi. This is a function of x and x is an independent variable, del x2 plus del 2 phi of y del y2 plus del 2 phi z and then del z2 plus v of x y z phi of x y z will be equal to energy times the wave function. So using the Laplacian operator, that is del square, we have seen that it is written as del 2 by del x2, or del 2 rather del 2 del x2, del 2 del y2 and del 2 del z2. So this is a Laplacian operator. So by it we can get this equation as h cut square by 2m del square phi, and this is a function of x y z, plus v, also function of x y z, and phi x y z equal to e times phi of x y z. One thing which is important here, that is this v and phi of x are function of x y z and x y z are independent variable. So as they are independent variable, so we can use the change of variable. So let us look into our cubical box, that is we define v of x y z equal to 0, just like the previous part where 0 is less than x less than L and 0 is less than y less than L and 0 is less than z less than L. And v of x, y, z tending to infinity otherwise. So now these two statements means that the potential inside the box is 0 and the potential outside the box is tending to infinity. Now what is the consequences of this? Just like the 1D case, the wave function phi must be 0 everywhere outside the box. Because the wave function must be continuous, phi must be 0 at all the boundaries by which we get the boundary conditions. And inside the box, the potential V equal to 0. So the time independent Schrodinger's equation simplifies to minus h, or rather just let us copy it to save our time. We will get this part. So if our V is becoming 0, so this part is now gone and the remaining is this one, just like our 1D case. Now as we said that this phi is dependent on xyz and xyz are independent variables, so we can use the change of variable. So let us take phi of x, y, z equal to, let us take this as x, y, and z. So what is here, the capital X is a function which is dependent on only x, and y is a function which is dependent on only y, and z is a function which is dependent on only z. So now if we put it into our equation, substitute, then we will get that minus h cut square by 2m. So in this here we would rather write only phi, because it is a function of x, y, z, or we have to write it as phi or phi of x, y, z. We cannot write phi of x directly. So this will be like this, and then if we derivate this one, partial derivative, then we will get y of y, z of z into del 2 x of x whole upon del x2. And similarly that capital X of x, capital Z of z del 2 capital Y of y del y2 plus x of x, y of y, then del 2 capital Z of z del z2, and then here we are getting e into x of x, y of y, and z of z. So now if we divide this left part by right part, then we get minus h cut square, or let us zoom it into minus h cut square by 2m into 1 by x of x del 2 x of x del x2 plus 1 by y of y del 2 y of y del y2 plus 1 by z of z del 2 z of z del z2, and then in the right side we get only e after dividing. So now let's rearrange this as, we'll just copy it from here itself. Just copy it here and paste it here. So this part will come, and this will be equal to negative time of 2me whole upon h cut square. So in this we can see that the first term only depends on x, the second only on y, and the third only on z, and the right side is a total constant. The only way this equation can be true for all possible values of x, y and z is if each case of three terms on the left side is also a constant. Let's call this constant as minus kx square and then minus ky square and minus kz square respectively. So it is becoming 1 by x del 2 x of x upon del x2 equal to minus k suffix x and whole square. And similarly, just copy this one. And now we'll change these things. So this will be y of y, and this will be 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 y, and this z, here it will be z, 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 and here suffix z. So this we are getting. And so comparing the above equation with this, we are getting minus k suffix x square minus k sub y square minus k sub z square equal to minus 2m energy by h cut square. So this gives us a crucial link between the k values and the total energy. So now the total energy is becoming h cut square by 2m into kx square plus ky square plus kz square. So now we have successfully broken the 3D problem into 3 independent 1D problem. So solving the 1D equation by analogy, we can say that it should come like this. When our function was del 2 phi of x, this is a 1D case. We are just comparing it. Del x2 was equal to minus k square, and this was phi of x. Then our general solution came as phi of x equals a sin kx plus b cos kx. It was like this. So by similarly we can say that for this case it will be x of, now this is 3D case, x of x equal to a sin of kx x plus b cos of kx, that is suffix x, and then x. Now this is 1, and then applying the boundary condition, that is x of 0 equals 0 and x of L equals 0, we get k of x equal to nx pi by L. So if we first put that 0, then we are getting b equal to 0, and then the equation is reduced to only this part. And when we are getting that L as x, then we are getting that a sin kxl equal to 0. So certainly a cannot be equal to 0, that is arbitrary constant, and we have discussed that why k cannot be equal to 0. Therefore kl should be equal to nx pi. So from there it is coming that kx equal to nx pi by L. So similarly, for the second part, that is, let us just copy this one, whole thing. Just change these things. For the y part, then this will be y, this will be y, and here it will be y and y. We can take a and b in both the cases because those are arbitrary constant, and I have said that we need not to care about that arbitrary constant because those are just arbitrary numbers. So we got this, and after this one, let us just copy and we'll paste it here. So this is the third one. Just will change this functions z, 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 and here it will be z, it will be z, z, it will be z over here and z here, and z, z. So this we are getting. Now as we know that what will the value of n? So nx equal to 1, 2, 3 and so on. Similarly ny will be equal to 1, 2, 3 and so on, and nz equal to 1, 2, 3 and so on. So now we will be deriving the final energy eigenvalue. So how we'll do it? That is E equal to, we got h cut square by 2m into kx square, ky square and kz square. So now we will substitute it, the k value that we got in this equation. So it brings us to energy equal to h cut square by 2m, and this will be nx square pi square by L square plus ny square pi square by L square plus nz square pi square by L square. So it gets simplified to like this, h cut square by 2m, and we are taking L square common and also pi square common. So we are left out with nx square plus ny square plus nz square. So this is the final eigenvalue for the energy, and now we will be deriving the final wave function, that is with the normalization. So let us just mark it. So this is eigen value. And now the derivation comes for the final wave function, that is eigenfunction. So we have seen that phi of x, y, z equal to x of small x and then y of small y and z of small z. So now if we consider phi of nx comma ny and nz, then we get ax sine kx x. So here we are considering ax, so let us just write ax over here, so to avoid our confusion, and then bx, and here ay, by, then here az and bz. So ax sine kx and then x into ay sine ky y and then az sine kz into z. So this is the final thing that we are getting. So if we combine the constant, that is ax, ay, az, and multiply it and make it as a single constant, then we can write it as a. So nx, ny and nz equal to a into sine of, now we will substitute the value of kx, ky and kz respectively. So this will become nx pi x whole upon L sine ny pi y whole upon L and sine nz pi z whole upon L, sorry. So this will be becoming like this, where we will just write a equal to ax, ay, az. We have considered this. So now to find the value of constant a, we use the condition that the total probability of finding the particle in the box is 1, that is normalization. So now we will integrate this inside the box. So phi square dv equal to 1. So it implies 0 to L, 0 to L, 0 to L, and then phi square will integrate with dx, dy, dz equal to 1. As those are the independent variables, so we can separate it all. Therefore, we write it as a square into 0 to L sine square nx pi x by L dx into 0 to L sine square ny pi y by L dy and 0 to L sine square nz pi z by L, and here dz equal to 1. So now if we substitute the value and integrate, then we will get, I am not going into the integration, so it will take time. We have done it in our previous lecture. So we will get here L by 2 for the first one, again L by 2 for the second one, again L by 2 for the second one, for the third one, and which will be equal to 1. So now we can say that A is equal to, or rather a square equal to 8 by L cube. So it simplifies to a equal to square root of 8 by L cube, or we can write it as 2 by L whole to the power of 3 by 2. That is also possible. So let us just write it as a equal to 2 to the power of 2 by L whole to the power of 3 by 2. This is same as the previous one written. So the final normalized wave function, that is the eigenfunction, is phi of nx ny and nz equal to square root of 8 by L cube into sin nx pi x whole upon L into sin ny pi y whole upon L and sin nz pi z whole upon L. So this is our final eigenfunction. So let us just put it inside a square box and mark it eigenfunction. So now the equation for degeneracy we'll see. So these are all we just got from here, that this is the eigenvalue and correspondingly this is the eigenfunction. So now we will go into equation for degeneracy. So what is degeneracy? Degeneracy occurs when different state, that is different set of quantum numbers, have the same energy. So let us use our final energy equation, that is E of nx, ny, nz equal to pi square h cut square whole upon 2ml square nx square plus ny square plus nz square. So now for simplicity, let us write this thing, that is pi square h cut square by 2ml square as E naught. So do not think that this is the this is n equal to 0, that is E naught. We have just written this part for our convenience equal to E naught, so that we need not to write it more and more times in our equations. So for ground state, that is example 1, for ground state, the lowest possible numbers are nx equal to 1, ny equal to 1, nz equal to 1. Therefore, we are getting energy of 1, 1, 1 as E naught into 3. So that is 3 E naught. So is there any other combination of nx, ny and nz possible? So the answer is no. So therefore the degeneracy of the ground state, degeneracy of ground state equal to 1, or that is non-degenerated. non-degenerate, because degeneracy means, as we have discussed, the different set of quantum numbers have same energy. So here only one set of quantum numbers has the energy. So now let us look into first excited state. First excited state, or in simply first ES. So in first ES, the next lowest sum of squares possible are, let us take nx equal to 1, ny equal to 1 and nz equal to 2. Therefore, the sum becomes, if we consider put it inside this, so it becomes 1 plus 1 plus 4, that is 6. Therefore, energy of 1 comma 2 equal to 6 E naught. So is this combination possible for another way, by another way? Yes, that is possible. Nx equal to 2, ny equal to 1 and nz equal to 1. So here also energy of 2 comma 1 comma 1 equal to 6 E naught, and also if we see, then nx equal to 1, ny equal to 2 and nz equal to 1. So here also we will get E of 1 comma 2 comma 1 equal to 6 E naught. So we can see that for different set of quantum numbers we are getting the same energy. So this is called degeneracy. These are three different wave functions that all have the same energy, that is E equal to, or the energy equal to 6 E naughts. So these all represent their state. If we see the state 1, so state 1 represent, that is 1 comma 1 comma 2 represent the wave function, that is phi of, in the suffix let us write 1 comma 1 comma 2. So this is a different wave function. And for the state 2, we have to consider 2 comma 1 comma 1. It represents phi of 2 comma 1 comma 1. And thirdly, we have taken 1 comma 2 comma 1, which represent another wave function, that is 1 comma 2 comma 1. So we can see that there are three different wave function that all have the same energy E, that is 6 E naught. So this is degeneracy equal to 3, or we can say it as 3-fold degenerate. Degenerate. So one more thing that we need to take care about, that what if our box that we have considered as cubical was not so. So let us suppose that our this x-axis length was, the vertex on the x-axis length was Lx, and the y-axis vertex length was Ly, and z-axis vertex length was Lz. So where difference would have arrived is here, in the energy. In the energy, we couldn't have taken this L common. So here it would have become, let us just make a condition that if L, X, Ly, Lz are vertex length and condition Lx not equal to Ly not equal to Lz. So those three are not equal to each other. Therefore, we would have got kx equal to nx pi by Lx and ky equal to ny pi by Ly and kz equal to nz pi by Lz. So our energy, that is the eigen value, would have become E equal to h cut square pi square by 2m into nx square by lx square plus ny square plus ly square plus nz square by lz square. So in this case, the energies for 1, 1, 2, 1, 2, 1 and 2, 1, 1 that we have taken this case, the energy would not be the same because the lengths of the vortex are different. This proves that the degeneracy is a result of symmetry in a system, that is, if and only Lx equal to Ly equal to Lz equal to L, then only the degeneracy exists. So thank you for watching this lecture. I hope you have understood. See you in the next one.